Hello everyone, sorry for my voice. I'm sick like the 2 weeks, and today I'm going to take you a journey about the dark side of the computer vision. We are going to explore what happens when the state-of-the-art object detection models like RFDTR, which we are examined in this video, face real-world harsh conditions and discover some surprising insight about why classical methods, fundamental methods, and modern transform spots struggle in ways you might not expect. Let me start with our challenge. We want to detect everyday indoor objects like cups, spaces, people. And here's the twist. We are doing with these no ground truth labels and no training. We are taking pre-trained models straight out the box and throwing them at the worst possible conditions like low light, blur, occlusion, and dramatic scale changes, etc. Why does it matter? Because in the real world, your robot does not get to ask people to turn on the lights or hold still for a perfect photo. We need to understand where and why our best models fail and see how they compare to classical computer vision approaches. We are comparing three approaches, one classical computer vision pipeline fundamental methods I built from scratch, the two original RFDTR transformer, three and my improved version of the RFDTR. So let's talk about the RFDTR first. This is a transformers-based detector that builds on the RFDTR. Excuse, pardon me. This builds on the DTR instead of the traditional CNN pipeline with anchors and non-maximum suppression. It uses a CNN backbone, feeding into the transformer that directly predicts 100 object queries. RFDTR's key innovation is adding the receptive field blocks with dilated convolutions before the transformers encoder. This expands the receptive field without increasing the computational cost, which should help with the small and occluded objects. It's pre-trained on Coco with 80 categories and works out of the box. Here's the comparison with the improved RFDTR and the original one. Improved one, I use Clahan gamma correction because it restores contrast and enhance details in the dark images. I use dual scale resolution and I use adaptive auto thresholding for confidence threshold to adjust dynamically to the lighting conditions. And here on the other side, I built a classical computer vision pipeline, the fundamental methods from six core components, HO, CMM for person detection, also an adaptive thresholding for counter extraction, can edge detection, HSV color segmentation, shift key points with DB scan clustering for textured regions, and selective search for object proposals. Each component targets different visual cues, but as we still see, they each have critical failure model. Like an HOC and CFM fails in low resolution, outside adaptive thresholding collapses in the dark, HSV segmentation collapses under low saturation, etc. Here's my data and the evaluation setup. 65 photos, 50 photos from my mobile phone, 6 from the data set publicly available, and 9 from them AI generated photos. Both photos in indoor and outdoor. RFDTR and the improved version failed in 6 scenes. That means I try to take 65 photos in different scenes like low resolution, uh, uh, con low brightness, etc. So 6 scenes is a large number, and 40 scenes RFDTR improved clearly outperform. That's clearly outperform to our original version. And as I said before, there is no labels and no training, and we compare three systems. Here's the failure cases. In dark conditions, RFTTR completely misses a glass on the table. There is actually two glass on the table, but you can see there is low contrast and dark image. And In the dark and blurred image, it cannot determine anything, and sometimes it mislabels objects or get confused by the reflections and shadows. Uh, as you can see, there is a bag, but it mislabels as a dog, and there is a door, it mislabels as a refrigerator. But the fundamental methods, it's even worse because it detects everything and nothing at the same time. This is meaningless. The key insight here is the both approaches fail, but they fail in different ways. Classical methods suffer from the threshold drift and lack semantic understanding, maybe using k-means for these photos and knowing the cluster numbers is can get better the fundamental methods, but RFDTR has semantics but struggles with the contrast collapse and confidence calibration. As you can see in the left side of the left photo, I have a glass in my hand, but it cannot detect the glass and it mislabels the couches as chairs. Here's in the dark image, it cannot find the glass, but fundamental methods to find everything, it's meaningless. In here, there is a good image because fundamental methods find the dark cup in laid down in the table, but RFDTR cannot find the dark cup laid on the table because it's different angle. It's a tilted cup and it's dark, and this image is a low resolution. RFDTR is not working well in low brightness, low contrast, especially in the low contrast and high blur. And in sometimes in high blur cases, it finds especially the photos with the cars, but in blurs with the dark. High blur in the dark images, it cannot detect anything and mislabels the object in high brightness or the far distances. Here's the improve versus original photo. As you can see, there is a lot of people, but original one cannot detect all of them, but improved one can detect all of them and the cars. Also, there is a couch and the cups in the dining table, but original one detects one couch, or improved one detects two couches, and original one cannot detect the cups, but improved one can detect the cups. Here's the potted plants. Original one and the improved one can detect all of the potted plants, but the trucks, original one cannot detect the trucks, but improved one can detect the trucks. Also, improved one can detect a little bit of showing the potted plant as well. So there's a lot of cups and the couch and the dining table photo, but uh, original one misses three cups. Improved one misses only one cup. It cannot detect the low contrast cup as well, and it can detect the couch. Improved one can detect the couch. Here's a tricky photo. I try to hide behind the cups and the dining table. Original one cannot detect the chair, couch, and other cups and me, but improved one can detect the chair, couch, me, and all the cups. Here's a AI generated photo. I try to camouflage the cups, but in small version of the cup, uh, improved one can detect them, but original one cannot detect the uh, small one. So, dark small objects, blurred ways, or occluded or low gamma scenes, original RF misses the cups, multiple wrong boxes, and confused suffrages. But the improved version cup detects cleanly, correct localization, and isolated only real objects. So, without retraining or labeling in a single image, I developed an improved wraparound RFDTR that significantly boosts the performance. I use Claha plus gamma correction to restore contrast. I use multiscale inference instead of 600 pixel resolution. I run 600 and 1000 pixel and then merge the results. I use adaptive thresholding uh, with outsource method, and I use smart NMS to non-maximum suppression. As you can see before, the improved version detects more traffic lights and cars with a higher confidence in indoor since it finds objects the original completely misses, and the cab image it cleanly detects the small cabs. As you can see, there is explanation of the fixes why I fixed them, like Claire plus gamma correction because it's expand the histogram and uh, relo is survival. That's neurons is become meaningful. There is a comparison with the RF DTR with the fundamental methods. This comparison reveals something profound about the nature of these two approaches. Classical computer vision approaches has zero semantic prior. It relies purely on pixel level cues with no understanding what a cap or what a SOA means. It's deterministic and interpretable, but brittle when the real world condition violate its assumptions. RFDTR has strong semantic priors from the COCO training. It knows what objects look like and viewpoints and scales, but it's vulnerable to distribution shift. When statistics differ from the training data, its confidence calibration breaks down. The key insight is pre-trained SODA models aren't enough by themselves, they need intelligent engineering around them. But here's the crucial point. You don't always need the retraining or new labels. Smart processing can unlock substantial improvements like in here. So, yeah, classical computer vision approaches brittle thresholds fails on the real world, so it needs fine tuning and it needs the knowledge about the image. But RFDTR can doesn't need knowledge about the image, but it fails on the edge cases like the dark image, blur, dark image, or low contrast, etc. So classical vision pipelines are brittle. RFDTR generalize better but not robust by default. Post-processing can significantly improve the pre-trained models. So what did we learn? Classical vision pipelines are brittle. In real-world variants, the thresholds works not in the fails in the practice. Even the state-of-the-art transforms need tuning for edge cases. Semantic understanding isn't a silver bullet. Failure analysis matters more than the good results. Um, Deliberately creating the challenging scenarios, we expose the model assumption. So we can find the practical solutions. And finally, traditional computer vision and deep learning each have blind spots. The future lies in the combining best of both semantic understanding from the transformers with dynamic image aware tuning from the classical methods. Thank you. I am happy to take questions. You can find the code and the report in under the video link.